Welcome back. We're going to continue our discussion on the first reaction in the topic of aromatic electrophilic substitution reactions. Okay, now the first reaction we're going to look at is halogenation of benzene. Okay, now we know this is benzene. Now that's reacting with Cl2 slash FeCl3. Now I said you will have three reactants. One of them is benzene. The other two react among themselves to produce your electrophile, which then reacts with the benzene to produce the desired product. Now, keep in mind, whenever I give you Cl2 FeCl3, the first thing you are going to do, now again, you do not have to remember this, like you do not have to do it all the time because you're not going to be doing mechanisms all the time. So the chlorine, if you're starting with Cl2, the iron would also contain Cl. If you start with Br, then the iron would contain Br. Okay, so what happens is these two react and they produce Cl plus and FeCl4 minus. What has happened here is that one of the Cl has gone to the iron, and in the process the Cl that's lost a bond gets a positive charge and the iron gains the Cl, so the iron gets the negative charge. Okay, now what happens here is this is your electrophile. I am going to circle it in a different color. This right here is your electrophile. Okay, let me do something else so I don't need to come back to this topic again and again. So let's say I change my color. Say I started with Br2. That means I won't use FeCl3. Instead, I would use FeBr3, and I would produce Br plus FeBr4 minus. Okay. Now, for the purpose of this particular reaction, let's just choose Cl plus and stay with it. Okay. So what happens here is, now I prefer this structure of benzene to start with, and you can also do the same. Now this reacts with your Cl plus. Keep in mind, we have to first generate the electrophile. This right here is your electrophile. The electrophile reacts with the benzene. Now how does it work? Well, basically the double bond goes and bonds with the Cl. Okay, so what does that do? The bond, the double bond here is used as a connecting bond to connect this carbon with the Cl. Okay, the rest of the bonds remain undisturbed at this point. Now keep in mind, this already has a hydrogen. Right now I'm going to switch color here. Okay, this double bond has now connected this carbon and the Cl. But keep in mind, the Cl had a positive charge, and I've told you previously that every time you move a bond, the tail of the double bond gets the positive charge. So essentially the positive charge from the Cl is now transferred over here. Okay, now you can draw resonance structures. Okay, so which means let's change some colors here. I guess I'll get the green. Now this bond, you cannot move the Cl, but you can move the positive charge. So basically you can now move, we have moved the double bond. So what will happen to our, if the bond is moved here, okay, sorry, for some reason it does that. So the positive charge would now go to the tail of where the bond has moved, right? This stays here. This is not something new. We did do this previously when we were learning aromaticity. So now this can move over here, which means now our new resonance structure is HCl, right? So you can have variety of resonance structures, or you could, so basically that means you could have, right? So you also keep in mind, so these are the three resonance structures of your compound. I'm just going to redraw just this one to complete the product. Okay, let me get my black color back. Okay, so these are the resonance structures. I'm just going to redraw where we started again. Okay, now to re-establish the product, the FeCl4 minus, which is a base, because as I said, anything with a negative charge is a base, that comes and grabs this hydrogen, which means the hydrogen now comes back here as a bond, which would lead, as I said, the bond coming into the ring is equal to a negative charge, so we have a positive charge, so they cancel out. So that means our product would be, we got our ring back, and we got our Cl. This hydrogen is now gone. Okay, it's gone with the ring. Okay, so you get your product. Okay, so we started with this, with just plain benzene ring, and we ended up with the chlorinated benzene ring, which is called chlorination of benzene. Okay, so now these are your resonance structures. Okay, now similar to what we did earlier, this is a very, very classic idea, and that is Friedelcrafts alkylation. Okay, if you don't know this after you graduate my class, it probably makes no sense if you didn't know answered on how to do these things. Okay, now I could easily change the CH3 to a different one, okay, which we will also see in upcoming versions. Okay, so again, as I said, we're reacting this with benzene. Okay, so CH3Cl reacts with your AlCl3. As I said, you don't always start with an electrophile. You produce the electrophile during the course of the reaction. So if you're starting with Cl, the Al compound, the aluminum compound, should also contain Cl. So what do you produce in the context is you produce an electrophile, CH3 plus, and you produce AlCl4 minus. Now all you have to really remember is whatever you're starting with, if it's an alkylation, that means you put the positive charge on the alkyl group. Okay, and then you will also see acylation. So we're going to start with our benzene. Again, I'm starting with this as my starting material. This reacts with your CH3 plus, right? Now, how do we go about it? How we go about it is exactly how we went about on the previous case. Okay, actually make it more clean. Okay, so let me get a different color. So we are going to move this bond and connect it to the carbon. That's the part of this group right here. So these are not disturbed. So we have connected this carbon to the CH3, right? Keep in mind, it also has one hydrogen already. And so is this. This has hydrogen too. Okay. Now, because this bond is used to connect this carbon with the C, this carbon should get the positive charge. The tail of the double bond always gets a positive charge. And you can write the resonance structures, like you can move this over here and then move the positive charge here, and then just like I did on the previous case, I'll draw one just for your knowledge purposes. I move this bond here. That means that's one of the resonance structures. So the bond is now here, so the positive charge is now here. What does that mean? That means that you can also have, you can shuffle bonds while you're doing this process. Okay, so this is one of the resonance structures, and you can keep going. This can come here, and then the positive charge can come over here. So I don't want to go back and redo every resonance structure I did in the previous compound. So what happens now? Let's rewrite our starting material in a different color. Okay, so I'm going to just rewrite this one of the starting resonance structures again. So this is what we have. Keep in mind, these compounds already have a hydrogen, right? Now again, the AlCl4 minus is the base. Okay. Let me change color again. That comes and grabs this hydrogen with it. And in the process, the hydrogen, the bond comes back here into the ring, only the hydrogen bond, okay? The bond connecting the carbon and the hydrogen, the bond comes back in. So that's equal to a negative charge. It neutralizes the positive charge that's there on the ring, which means we are going to have basically this as a product. So this is alkylation, okay? Which means you just basically have to remember that add a positive charge to this CH3 in this case. Now, what if I had given you, like I said, instead of a CH3, I'd given you CH3, CH2Cl plus AlCl3. Well, that would be nothing but CH3, CH2 plus, that's your electrophile, plus AlCl4 minus. This is always constant. So this is always going to be constant in a Friedelcrafts alkylation, this AlCl4 minus. So this is your electrophile. Now that reacts with the benzene ring and the process continues on. Okay, I want to do one more reaction as part of this video because I don't want to make the video too long. So this is Friedelcrafts acylation. It's almost the same thing as previous case. So you start with the benzene, and so your CH3COCl is your acyl compound that reacts with AlCl3. Now again, the Cl would go with the aluminum, which leaves you with, please don't put the positive charge on the oxygen, please put it on the carbon, okay, plus AlCl4 minus, okay. Now that reacts with our benzene ring. Seems like a recurring pattern, huh? See, that's why I find these very, very fascinating, because you only have to know how to do one, the remaining all falls in place. Okay, so CH3, C plus O, right? As with the previous cases, you know what to do. The double bond attaches itself to the carbon. Keep in mind where you move your arrow. Just don't move the arrow and attach it to any carbon or oxygen as you wish. Move them to the carbon containing the positive charge. That's where it connects, okay? So what does that mean? Means let's draw this now in red and draw the group in blue or some other color so you can see the transformation better. Okay, so I have attached this carbon with this carbon, okay, and the O, and this also contains the CH3. Okay, you can write the CH3 here. Keep in mind the carbon and the oxygen are both attached. The CH3 and the oxygen are both attached to this carbon, and the positive charge goes here. Okay, what students tend to do is they draw the CH3 here, and that's not correct. You're attaching this carbon with this carbon, not the CH3. Okay, so keep in mind again, you have hydrogens in both places. Now let's switch colors. So the AlCl4 minus is a base that comes and grabs this hydrogen, and in the process this bond comes back into the ring, which neutralizes the positive charge. Again, you could draw resonance structures for this molecule, which I am not going to, because I want to keep a little bit of autonomy on your part to try some of these structures yourself. So let's go ahead and draw the product, which means, so your CO, keep in mind the CH3 is here, and then the bond comes back, and that's it. Okay, so this is your product. So all you have to say, instead of CH3COCl, say I had given you CH3CH2COCl plus AlCl3, then, you know, it's very simple. All you got to do is CH3, CH2, C plus O. plus AlCl4 minus, right? So this is the R value that I was referring to. The R could change, but the positive charge always ends up on the carbon, okay? All right, so stay tuned. I got a couple more reactions that I want to walk you through before we actually go and talk about the effect of an added substituent, all right? So stay tuned.